Right, so Richard Samuelson is going to talk about, he's going to give a talk on the subject towards a compositional framework for convex analysis. So take it away.
Okay. Can you hear me?
Yep.
Okay. So this talk is about how category theory might inform the study of convex analysis. And the main source for this talk is going to be Rockefeller's sort of introductory textbook, Convex Analysis, which at the very end of which he explores a very interesting compositional approach to convex analysis. We're going to sort of maybe formalize this a little more. So the object of study here is the convex function, but we're going to start by talking about sets and relations. A relation from X to Y, where X and Y are sets, is just a subset of the Cartesian product X times Y. Relations can be multiplied to each other using this formula, and this is called the relational product of two relations. And in fact, using this as a definition of composition, we can form a category out of sets and relations. And in fact, this category is a hypergraph category called rel. So one thing that's interesting about hypergraph categories is that they are morally undirected. By this, I mean that if you think about a wiring diagram in a hypergraph category, you can sort of profitably forget, if you take a morphism or a box, you can sort of profitably forget which wires are going in and which wires are going out, and instead regard all the wires as just an interface to your box. So this is from Fong and Spivak's article, Hypergraph Categories. And here they argue that the wiring diagrams on the right are sort of most appropriate to hypergraph categories. And as you can see, they're undirected. In this talk, we're going to sometimes use the second type of wiring diagram, and sometimes we're going to use the fourth. And I'll be clear when I'm using the second and when I'm using the fourth. Those are sets and relations in general. A subset of Rn is called convex if for any 2 points in the set, the line segment between those points is contained in the set. That's the definition. So we'll define a convex relation from M to N to be a convex subset of Rn plus N. This convexity is preserved by the relational product, and so we can think about a subcategory of rel, which we'll call CX rel, and this is a prop of natural numbers and convex relations. And this is also a hypergraph category. So this is from Wikipedia. The set on the left is convex, and the set on the right is not convex because you have two points in the set such that the line segment between those points is not contained in the set. So hopefully this is helpful. We started with convex sets because there's an intimate relationship between convex sets and convex functions, which is not intuitive. So if you have a function defined on Rn and which takes values in the extended reals, we can define the epigraph of this function to be all the points which either lie on the graph of the function or above. And we'll call a function convex if its epigraph is a convex set. This is not the usual definition you see of a convex function, but it is equivalent to the usual definition, which involves lambdas. And because this relationship is one-to-one, we can think about convex functions in terms of their epigraphs. And in fact, we can even, this is an image of the epigraph of a convex function. So the graph of the function is the blue thing, and the epigraph is the green thing. We can use epigraphs to compose convex functions in a way which is a bit unintuitive if you haven't seen it before. So this definition is due to Rockefeller. If you have, first I should define a convex bifunction. So this is the central object of study. A convex bifunction is just a convex function of two variables. So again, we're going to think of these as morphisms in a prop. So yeah, a bifunction from M to N is just a convex function defined on the product space. Rockefeller says that we can multiply convex bifunctions by taking the relative product of their epigraphs. And so this is a wiring diagram representing the multiplication or composition of two convex bifunctions via their epigraphs. That white circle is the white circle from graphical linear algebra. It means that the input has to be the sum of the outputs. So the result of this is going to be the epigraph of a convex bifunction, which is called the product of the two bifunctions. Now, this is cool, but maybe not the most intuitive. This doesn't make a lot of sense. You can also think about multiplication in terms of this formula. And this is an equivalent definition. And I think this is the definition that Rockefeller actually gives, where the product of the bifunctions is you take their sum and then you infamize over the middle variable using this sort of tricky logic involving positive and negative infinities. And if you take this as a definition of composition, you can form a category of natural numbers and convex bifunctions. And this is also a hypergraph category. And we call it CXBIFN. So that's cool. But why is this category interesting? I'm going to try to motivate it by looking at an algorithm, which is a very important algorithm, which has been considered in at least one other talk, which is the Kalman filter. And we'll see if thinking about it categorically improves our understanding of why this algorithm works. So the Kalman filter is both, it specifies a problem, and then it's a linear time algorithm for solving this problem. So we have these random variables, which are indexed by time, and they're called states. And these other random variables, y's, which are also indexed by time, and they're called measurements. And the idea is broadly this. We want to know about the states, but all we can see are the measurements. So specifically, a Kalman filter is dictated by these equations. And these equations totally specify the distribution, the joint distribution of all the random variables, because we have this Markov property, which says that if we know the state at time I, then we can forget all the previous states. Our knowledge of the next state is only determined by the state at time I. So you can do a lot of things with this setup. One thing you can do is what's called the filtration problem, which says basically this. We've observed all the measurements up until time n, and we want to know the state at time n. So a common example of a Kalman filter is you want to know where like a rocket is. And so the state would be some combination of location, velocity, acceleration, and then the measurements would be kind of noisy measurements of these three properties. And so you sort of have these bad measurements of the location, velocity, and acceleration of your spaceship. And you want to know where the thing actually is at time n. We can, and so the Kalman filter says that you can solve this in linear time just by iterating two steps, which are called the, I think, state extrapolation step and the state update step. So we can reformulate this as a convex optimization problem. It's not completely intuitive that you can do this, but it does work. So we'll define the following bifunctions. The first is going to be called the state at time 0. And all these letters come from the equations in the previous slide. The state at time 0 will have a bifunction called measure and a bifunction called predict. And then we'll use these to form this odd-looking objective function, which we'll call the state at time n. And the idea is the solution to the filtration problem is the unique minimum of this objective function. So we've turned our sort of statistical problem into a convex optimization problem. And then what we're going to do is we're going to represent this objective function using a wiring diagram. And here we're going to use the fourth type of wiring diagram, the undirected kind. So what you're looking at here is the sort of left tip of a very long tubular looking wiring diagram. So you should imagine this being extended for Y3, Y4, Y5, all the way through Yn. And we want to do is we want to compose all of these morphisms to form our objective function, which we'll then minimize to get our answer. And the Kalman filter says, well, you don't have to do it all at once. You can actually do this just two at a time. So these are the two steps that you iterate in the Kalman filter. First, you take the current state and you compose it with the predict function to get a pre-measurement. So for example, the first step would be you take the state at 0 and compose it with the predict function, bifunction, to get a pre-measurement state at time 1. This is called the state extrapolation step. And then you take the pre-measurement state at time 1 and combine it with the measure function and the observation y1. And you get the post-measurement state at time 1. And if you just do this over and over again, eventually you've composed all your morphisms and you have your objective function, which is a function, a fairly small function, and which is very easy to optimize. And you can see maybe why this is a linear time algorithm, right? Instead of doing everything at once, you can just sort of do this in steps where each step is indexed by time. And the reason I use this as an example is because I think one of the advantages of this compositional approach to convex optimization is it helps make sense of these algorithms, which are usually specified like algebraically, but I think which make a lot more sense graphically, right? If you have a wiring diagram, which is sort of shaped in a kind of rational way, you can decompose the composition of all your morphisms into a bunch of smaller problems, right? And the whole thing goes faster. Okay, so we're going to talk next about the Legendre transform, or Legendre transform. So the Legendre transform of a convex function. So like every convex function can be transformed into another convex function defined on the same space via the Legendre transform, which is this kind of spooky looking equation here. This can be used. This transform can be extended to bifunctions via what Rockefeller calls the inverse adjoint operation. It's kind of a weird name, but it's called this because in Rockefeller's mind, this was composed of two operations, which produce a single transform. But we're going to think of it as just one. So a convex bifunction can be transformed into another convex bifunction through this formula. And the claim that I'm going to make is that morally, the inverse adjoint is an involutive endofunctor that takes convex bifunctions to convex bifunctions. Now, this is only true morally because it's only involutive up to a certain regularity property called convex closure. And sometimes it's not even functorial. So this is something that we need to work on. But there are certain subcategories of convex bifunctions where this thing does work and is functorial and is involutive. It just doesn't work on the whole category. It's somewhat frustrating. So an example of a sort of well-behaved subcategory would be this category of indicator functions. So we can embed. So a linear relation, from M to N is just a vector subspace of R n plus N. And these form a hypergraph category, using normal relational composition. We can embed this category into the category of convex bifunctions by mapping linear relations to what are called convex indicator bifunctions, which take a vector space and map it to the function which is 0 in the vector space and infinite outside of it. This is a very well-behaved, this category of indicator bifunctions is very well-behaved. And in this category, the inverse adjoint operation is precisely the color swap functor from graphical linear algebra. So you can think of the color swap functor as a special case of the Legendre transform. It's kind of interesting. And there are other subcategories where the Legendre transform or the inverse adjoint operation is well-behaved. But this is a good example. Another interesting subcategory is, well, I should say, I'll restart. So thinking of the Kalman filter as a convex optimization problem is a little weird because it's really a problem, like a statistics problem, right? Involving products and integrals of densities. And the fact that it can be reformulated into a convex optimization problem involving sums and infima of convex functions is not completely intuitive. nevertheless, there is this kind of magical correspondence between Gaussian probability and convex bifunctions. So here's an example. A Gaussian conditional distribution from n to n is a Markov kernel of this form. And these form a Markov category called Gauss. Intuitively, wiring diagrams in Gauss generalize Gaussian Bayesian networks. This is an example of a Gaussian Bayesian network. And what you should think of when you see this is that the nodes are wires. And if two nodes are connected by an arrow, then you have a morphism between those wires in the direction of the arrow. So this is sort of a dual representation of a wiring diagram, although not all wiring diagrams can be represented in this way. But every one of these corresponds to a wiring diagram in Gauss, as long as the conditional probability distributions are all Gaussian. We can embed this category into the category of convex bifunctions by taking the energy function of our conditional distribution, which we define here. And if we map conditional distributions to these, what we call energy functions, and I'm taking this term from statistical mechanics, you can embed Gauss into the category of convex bifunctions, quotiented by constant shift. So this category is the category of convex bifunctions plus or minus some constant. And this sort of quotient is respected by both the Legendre transform and composition. So that's cool. Maybe even weirder, there's this category of what we call Gaussian systems. So a Gaussian system on Rn is this kind of strange thing. It's a Gaussian system on Rn with fiber L, this is a subspace, is a Gaussian distribution on the quotient space, Rn divided by L. A Gaussian relation from n to n is either a Gaussian system on the product space or something we call a failure morphism, and write with the bottom symbol. Natural numbers and Gaussian relations form a hypergraph category, which we call Gauss-Rel. And your intuitive understanding here should be that wiring diagrams in this category generalize a type of probabilistic model called the Gaussian Markov random field. So this is a little more general than the Gaussian Bayesian network. And one common thing that is done in probabilistic modeling is you will take a Bayesian network and turn it into a Gaussian Markov random field. And the difference is that Bayesian networks are somehow directed and Markov random fields are somehow undirected. So this is an example. And again, what you should think about when you see this image is that the boxes are wires and two boxes are connected by an edge if those wires are connected by a morphism. But there's no arrows here. So it's a sort of undirected wiring diagram. The reason you can represent every Bayesian network as one of these things is because you can embed Gauss into our category Gauss-Rel, right? You can embed this Markov category, which feels like morally directed, into this hypergraph category, which is morally undirected. In the same way, you can represent Bayesian networks, which are directed, as Markov random fields, which are undirected. That's the intuition. These morphisms in this category Gauss-Rel, these Gaussian systems also correspond to energy functions. So a Gaussian energy function is a quadratic function of this form. And it's a quadratic function which has a minimum. So it can't go, the infimum of the function can't be negative infinity. And there's a bijection between Gaussian relations and equivalence classes of these energy functions. The equivalence class is again plus or minus some shift. And again, by mapping Gaussian relations to these energy functions, we can embed this hypergraph category Gauss-Rel into the category of convex bifunctions, quotiented by constant shift. And this is, what this means is that problems that you think of as probability problems, as long as everything's Gaussian, can always be rephrased as a convex optimization problem by taking distributions and mapping them to their energy functions. And this is a trick used a lot in statistical mechanics. So if you look at these energy functions, the inverse adjoint operations takes the energy function of a Gaussian distribution and maps it to what is called the cumulant generating function, which is the logarithm of the moment generating function. So that's how that operates on these energy functions. So that's it. There's a lot of further work that has to be done. One is that I said that this thing is morally a functor, but of course, it isn't actually a functor due to these little regularity concerns. So we want to figure out how to make this actually a functor. And one area, one promising looking direction is through is from a paper by Willerton, 2015, which thinks about convex functions as existing in a category enriched over the extended reals. So that's one direction that we want to extend into. And the other is, of course, to figure out why there is this weird correspondence between this little section of probability theory involving Gaussians and convex analysis. And two directions that look promising are through the study of cumulant generating functions. So I think not every, but to many probability distributions, there corresponds a convex function called the cumulant generating function. This is used a lot in statistics and in the study of generalized linear models. And these cumulant generating functions behave very well under affine transformations. And so, yeah, maybe there's this kind of like broader connection between probability and convex analysis via this cumulant generating function. And the other direction is through this thing called Maslov dequantization, which I don't entirely understand, but basically says that often you'll find this correspondence between systems defined over like addition and multiplication and systems defined over the tropical, I forget what it's called, tropical semi-ring of maximization and infimization. So this is what we're seeing with energy functions, where problems which are defined using products of densities and integrals can be transformed into problems defined using infimization and summation by mapping densities to these energy functions. So that's another direction of further work. I hope that made sense. Does anybody have any questions?
So are there any questions in the room? Okay.
Hi, thanks for the really cool talk. I was just curious what the monoid and comonoid structures are in convex bifunction category.
So you
like what the copy and delete, or sorry, not copy and delete, copy and like co-copy.
You do it through these indicator bifunctions. So you take the indicator of the set, which in rel is the copy and delete. So you can generally map.
Is the merge like the indicator bifunction of the sum?
No, the merge is the indicator bifunction of the merge in linrel, which is not sum. It's it's like a transpose of copy, something like that.
Okay, thank you.
Yeah, so every linear relation can be represented, and this is kind of weird, as both a convex set, but also as a convex function.
Thanks for the nice talk, Richard. So at the end, you sort of alluded to this, but when you said that the what did you call it? The inverse adjoint sends the energy function to the cumulant generating function. It got me thinking about exponential families, right? Which are this nice class of distributions used in statistics that have very well behaved cumulant generating functions. So I'm wondering whether you've tried to work out what happens in any other exponential families, or if that's a direction you're considering?
We haven't, but it is a direction we're considering, and it's something that we hope will bear a lot of fruit. But we've only really worked with Gaussian so far. Yeah. There's this thing called the saddle point approximation, which seems to suggest that if you try to do all these operations with cumulative generating functions, you end up with like approximate solutions instead of exact ones. So that's another direction. But yes, yes, we're thinking about working with sorry, I forgot what they're called, but yeah, the generalized, not generalized linear models, but yeah, that type of distribution, and hoping that it will bear fruit.
Okay, thank you.
Yeah, I have a question. Thanks for the talk, and this is great work too. I want to ask, it looks like this category of convex bifunctions, you can order them, right? So it forms a bicategory, like with the partial
Yes.
order on the Hamza.
Yes, and it's
Either
preserved by
upwards or
composition.
yes, exactly. So it looks a little bit like a bicategory of like spans or like enriched matrices, the kind of stuff such that monads usually give you something like categories or like metric spaces. So have you looked at monads in this bicategory and what they give you?
No, I haven't. Speaking of spans, our category Gauss-Rel that we mentioned later can be represented as a category of decorated cospans, where the legs are matrices and the decoration is a Gaussian distribution. This might be completely unrelated to your question, but it did come to mind. But no, I certainly haven't thought about monads in this category. But thank you for mentioning it.
Are there any further questions? Questions online? There are no further questions and no questions online. Let's record again.